Last one, testing for correlations between variables. So you're going to have two variables, x and y, right? X might be the number of leaves on the dandelion in the fall, and y might be equal to the number of flower heads in the spring. Typically, when you're coming up with testing your correlations, you're going to have x as the dependent variable, as the independent. So the one along the bottom, your x-axis is going to be independent, so it's going to be the one that is going to be influencing what is ever on the y. This is typically how we do them, unless your x has something to do with like height, altitude, depth, something that is typically seen vertical, then you'll put your x on the y-axis, or your dependent variable on the y-axis and your independent on the x. But typically independent on the x, dependent on the y. And again, these are showing correlations, and correlation is not causation, so we'll talk about that in a little bit. But just like to look at what some of these correlations would look like. Again, we're always testing our null hypothesis, which says there's no correlation between x and y. Our alternative is going to be opposite. There is a correlation between x and y. And so, looking at these graphs, here you can see what it'd look like if there was no correlation between your x and y. An r of 0. Your r values are always going to go from 1 to -1. You're never going to find anything outside of 1. Where your negative correlations is where you're going to see an inverse relationship. So as one gets bigger, the other one gets smaller. Whereas this one gets bigger, that one gets smaller. And so you get an inverse relationship or a negative relationship versus a positive correlation. As this one gets bigger, this one gets bigger. As this one gets smaller, this one gets smaller. And so, here's our lovely formula. Again, you will not need to memorize this formula, but you will need to know how to use it. So, to calculate this R value, to figure out if we have a correlation or not, you're going to take the difference between your sample and its mean for the x, times that by the sample and the mean for the y. And so if you have plant 1, you're going to look at, if we're using the dandelion one, you'll look at the number of leaves subtracted by the mean, and then the number of flower heads for that same plant subtracted by the mean for those flower heads. Okay? And you do that with all your samples. So if you have 10 samples, you'll have for sample 1, for sample 2, for sample 3, and you'll go through that. And then you'll add all those up. You're going to take the square root of the difference between your x sample minus the mean squared times the same for the y. Okay? For this, we're going to get a t value. So we get our r, and then we're going to calculate our t value from that r. So this is going to be our calculated t. Since we're using a t value, you're going to take n minus 2. So however many samples you have, minus 2 to get your degrees of freedom. And so to find the absolute value of r, you'll take the square root of your degrees of freedom over 1 minus r squared. So, again, this is looking at a correlation, not a causation. So if we're doing the dandelion flower thing, maybe the more leaves, maybe we see a positive relationship between the more leaves the plant has, the more flower heads it sprouts. Okay? Could be due to the leaves. Could be due to the soil, could be due to the light, could be due to lots of different things. But we do know that these two things are related. And so from this understanding, you can delve deeper into figuring out, is it the light? Is it the soil? Is it the leaves? And manipulate those things. So just be careful drawing conclusions from correlations because they are only correlations, right? Okay, so we get our absolute R value. This R square, it's known as the coefficient of determination. So figuring out your R square, if you have an R square of like 9, that is telling you, so you have an R square of 0.9. That is telling you that 90% of the variation that we see in our samples is due to this correlation. So if it is leaves and flower heads and you have an R square of 90, we're saying these two things are tightly correlated. Like 90% of all the variation we see is based on these leaves and these flower heads and how they're interacting somehow. It's not telling us what's going on, but it's telling us that like 90% of the variation that we see is based off of this factor, off of these factors, like whatever is making more flower heads and more leaves, 90% of that is based in that factor. Alright, so we can use regression lines to fit to the data, which will help us model this relationship. And so you end up like here with a bunch of data points. If you draw your regression line, you can make predictions about if you have a known value of X, what the Y is going to be, and vice versa with the Y and the X. So we can use regressions to model these relationships. So we're getting into ecological modeling here. Really, one of the most common ones is using a linear least squares regression, or a least squares regression, where we look at Y hat, this Y with the caret on it, we call it Y hat. This is going to be our estimated value of Y. So we don't know what the Y is, but we do have the mx plus b. Where you might have remembered this from algebra so many years ago. M is going to be your R value with your S over your X. So your rise over your run, right? So the vertical over the horizontal. So if you have it go up free and over 2, right? That's going to be your slope. That is what the M is your R times your rise over your run. Your B is going to be your y-intercept, all right? And so that is going to be based on your average of y minus the slope times your x. So you have an x of 5 minus your slope of 3 over 2 times r can get you your y-intercept based on that y mean. So here we have a data table looking at soil pH and species richness. And so we want to know, is there a correlation between the pH in the soil and how many different species are found in that area? And just to simplify this all down for you, the mean for the X is 4.86. The mean for the Y is going to be 44.7. So we had 10 samples. We added up all the X's to get 48.6 over 10, get 4.86. Do the same with the Y to get 44.7. Then we figure out our variance, right? And so that's going to be the difference between the x and the y squared summed up with your n minus 1. The n is 10, so it's going to be, for your x's, 5.164 over 9 to give you 0.574. For your y's, 130.1 over 9 to get you 14.45. Then take the square root of that so you can get your standard deviation. And then we can plug that all into our R formula here. Again, remember, R is always going to end up somewhere between 1 and negative 1. So here, again, x minus the x mean, y minus the y mean, multiply those together, add them all up, you'll get 24.38. The square root of your x minus your x mean squared times y minus y mean squared, add it all up, multiplied together, you end up with 5.164 for your x's and 130.1 for your y's. Take the square root, divide 24.38 by that to get an R value of 0.941. This is a really high R value. If you remember, here's an R of 1, here's an R of 0.9. We're somewhere in between here. So as our x goes up, so does our y. These things are highly correlated with each other. The pH and the species richness are highly correlated with each other. We know we had 10 samples. We're using our t, so we're going to calculate a t off of this. So we're calculating our t value to our t calculated to figure out what our t is. First, you want to get the absolute value of r. So if you have a negative r, if you have a negative correlation, you're going to go ahead and make that positive. So if we had a negative 0.941, it would still end up being positive because we want to get our t value, which has to be positive. All right. Again, degrees of freedom for a t is always going to be n minus 2. And then we're going to take 1 minus our r squared. So our r of 0.941 squared minus 1, or 1 minus that, over 8, and take the square root of all of that times our absolute r, and that'll give us a value of 7.865. If we match this up with our t table, we have 8 degrees of freedom. We go down to our p being 0.5, and this thing is a lot larger than that. We can actually look at the p-value of 0.001, so even smaller than 0.5, a lot smaller than 0.5. At p equals 0.001, you get a t-crit value of 5.03. 7 is much bigger than 5. We reject the null. So we are saying that there is some sort of correlation between these two. Okay. So we find our t-value. We're like, there's a significant correlation between these two objects, between pH and species richness. Now we can model this by using y equals mx plus b. I know you're like, I didn't know I was getting into algebra again. But we're going to. So to calculate your m, we want to find the slope, right? And the slope is going to be your r value, which in this case was 0.941, times your s for your y and over the s for the x. So the standard deviation of y over the standard deviation of x. And that's going to give us our rise over the run, right? So for y, it was 3.802. For x, it was 757. And so we're saying for every 3.8, Up, we're going to move over 0.757. Multiply that by our r, and now we have our slope of 4.726. The b, or the y-intercept, is going to be your y-mean. In this case, it was 44.7. So if we go back here, you can see the y-mean, 44.7, minus our slope, which we just calculated, times the x-mean. So we go back, here's your x-mean, 4.86, and that equals a y-intercept of 21.732. So with this, we can draw our line. And it lets us know for any given x, so we can have any pH, you can have a pH of 1, it's not even on this graph because we didn't get data for it, but you can have a pH of 1 and you can calculate or estimate what that y is going to be. Of course, it's not going to be identical, right? Because you can see here that not all these line up on this line. There is some wiggle room there. But it's going to give you a really dang close estimate, especially with an R of 9 anything. 0.941 is a really high R. So your estimation is going to be pretty spot on. It has a really high confidence interval. Okay, so things to know for the quiz. Given the equation for R, calculate both R and R squared for the data set. Devise the appropriate null and alternative hypotheses for a correlation. Given the formula for T, calculate the T, test the null hypothesis, draw appropriate statistical conclusions. We never prove anything. We can disprove the null hypothesis, but we never prove the alternative hypothesis. We never prove the null hypothesis. You can accept them, but you can't prove them, okay? Never do we say prove. Derive the formula for a regression line. So, talking about this, y equals mx plus b, being able to calculate your y, your b. Again, I will give you these formulas. Know that the y hat is an estimation of y. Graphed out on a scatter plot, plot a regression line on that same graph. Don't worry about knowing these two. The least squares is just that we are taking the square root of this to come up with our line. Not something you really need to know. And then the residual is basically talking about this space that is left over between our line and our data points. But that's not something I'm going to test you on, so do not worry about it. That's it for correlations and how to do a regression line.